Hi there and welcome to the screencast for Workshop 3 for 297 101 Statistical Data Science. So this week we're continuing our sort of journey in using ggplot to summarize data and produce charts, and we're going to be focusing on the distribution of a numeric variable, so what charts are appropriate for that. And we're also going to look at R Markdown. So instead of using an R script this week, which is a code first document, right? All the lines in the script are code, and if you want to add other things like comments, you have to do something special, like put the hash beforehand. An R Markdown document, on the other hand, is narrative first, or writing first, or text first, plain text first. And if you want to add code, you've got to do something special. Okay, so we're going to right-click and save the Lab 3 Markdown file, and I'm going to put it somewhere that I know where it is. Then I'm going to go into RStudio and load it up, right? So open, find the file, there it is there, and here it is. Okay, so here's a Markdown file. You can see that when I loaded it, the console vanished, and that's because the code that we'll be running will be written inside the R Markdown file, and the output from that code will be placed inline, which is kind of nice. We don't really need to use the console that much anymore. So you'll notice that this document is essentially plain text, right? So we have just some writing here about what we're doing today, but it's not completely plain. There are some extra bits added on, right? So we have this introduction line here, which looks as though it's a heading, the way it's written, and it has two hashes before it. So in an R Markdown file, a hash signifies a title. So one hash is a giant title. Two hashes is then, or a giant heading if you like, and two hashes is then a smaller heading. Three hashes is, if you like, a subheading. Four hashes is a sub-subheading. Five hashes is a sub-sub-subheading, and so on. Right, so if you know HTML, so what we're going to be producing from this Markdown file is an HTML document. You can kind of get a hint of that up here from this output command. We'll get to all of this stuff in a moment. And in HTML, there are 6 header tags, so H1 through H6, H1 being the giant one, H2 being a heading that's not a title, if you like, and then H3 being a subheading, and so on. So the H1 corresponds to one hash, H2 corresponds to two hashes, and so on. So if you've done any HTML, then that's where the relationship is. If you haven't, it doesn't really matter. All you need to know is more hashes, smaller title. There's other things as well. So for example, the like this here, you'll notice has been surrounded by two asterisks. Okay. And it's been rendered in a different color as well by the editor, and that's going to be bold. So two asterisks signify bold. A single asterisk signifies italics, which is a slanty text that's been pushed over a bit to highlight something. And three asterisks, of course, will be bold italics. We can also use a bunch of other things. So bullet points. So here's some bullet points down here. So they're just done with a minus symbol or a dash symbol. I like to put a space before it. I think you are required to put a space after, but just to sort of indent it so it looks nice in the plain text document as well as in the final document. So we've got headings, subheadings, sub-subheadings, and so on. And we can also have other formatted text. So you'll notice that here I've used the backtick. So the backtick, which we'll be using a bunch, so you need to know where it is on your keyboard, is in the top left above the tab key and below the escape key usually. And so a backtick signifies code. So this will be just rendered as code. So it uses a monospaced font, so a font where the characters are equi-spaced, whereas most text, of course, the characters aren't equi-spaced because an I, for example, takes up less space than a capital H, right? And so that's what the backtick is. We can also add R code. So here's some R code down here. And you can see that that unlike with an R script where you just write your code and you have to do something special for your text, in an R Markdown document, you just write your text and you have to do something special for your code, right? So the thing that you have to do special is you have to delimit a set of lines for code. And the delimiters are, again, this backtick. So it's 3 backticks at the start and 3 backticks at the end. That denotes a code block. And then you can optionally say what type of code it contains. So in this case, we've got a curly brace, and then R, and then a closing curly brace. That dictates that this code chunk is going to contain R code. Okay, so RStudio, the editor, of course, was originally designed for R code, but you can write Python code and various other types of code in here. Bash, scripting. We can see them actually under here. If we click this button here, which is the one to insert a new code chunk, you can see that the default is R, but you've also got Bash, which is a terminal. You've got D3, which is a JavaScript library for charting. You've got Python. You've got RCPP, which is a wrapper between R and the C++ programming language. So a lot of the packages that we're using in R will actually be written in C++. And then there's a bridge that goes between the C++ code and the R code that just makes it kind of a natural transfer. So those of you that are doing computer science that might be interested in this, if you're not, you can tune out for the next minute or so. So what RCPP does is essentially transfers the objects in R land, such as vectors of numeric vectors, for example, to an object in C++ land, which is a numeric vector, which will just be a standard, so an STL, standard template library vector of doubles. And it handles that transfer for you. So that in the C++ land, you can just use all the standard STL template library tools to manipulate that data. And it does so in a smart way that there's not even a copy often. So you're dealing with the underlying data directly, which is quite nice. We can also do SQL or SQL, which is a database language. We'll be getting to that in a little bit more detail next week. We won't actually be using SQL, but we're using something very similar. And also Stan. So Stan is a computing language for Bayesian statistics. So it's a statistical computing language for doing inference, essentially, and a bunch of other things via Monte Carlo Markov chain. Don't worry if none of that made any sense. We're not going to be using it. If you're interested, then that is used quite extensively in 161.304 at 300 level stats. Okay, so here's a code chunk. So we can insert one with Control-Alt-I. So if I do that on my keyboard now, you can see I get my code chunk. Okay, you can see that it's the editor has identified it as a code chunk and given it a different background color, which is quite nice. And it's also given us some controls up here. So the controls are settings. Okay, so there's a bunch of options that you can specify in your code chunks. We'll be looking at some of those later. Then we have this button here, which is run all the code chunks above this one, of which there's none, so that won't do anything. And then we have the play button for running the current chunk. So you can run the code lines line by line as per usual. Just put your cursor on the line and Control Enter will do that, or just hit run up there. But you can also do it all at once. So if I run that, then you can see that I get my tidyverse library loaded, and there's the output from Quakes. So here we're loading the Quakes data, and then we're having a look at the head of it, which of course is gives us the first 6 rows by default. Okay, if you want the last 6 rows, then we'd use tail. So tail Quakes will give us the last 6 rows. Okay, so maybe I could add a comment. So inside a code block, of course, then if you want to add notes inside the code block, that's a code block, so it's not expecting writing, it's expecting code, so you have to use the hash, right? So this is it's like having a wee R script embedded within the Markdown file. Now there's a couple of things you need to watch. So a couple of really common mistakes are accidentally modifying the delimiters here. And most errors that folk get with markdown files come from that type of thing. So if you accidentally, for example, got rid of one of the backticks at the end there, you can see that now the editor is saying, well, you've got a code chunk starting here, and it's then just run down to find the 3 backticks again, which is down here. Okay, so it thinks that all of this is now code, and we've got an error message here. Okay, so if you see this behavior, look for your end delimiters. So the other one is accidentally putting a space in front of the delimiter at the start. Okay, so that of course has the same problem. This is now not recognized as our code. We get no errors, but it just won't be run. Okay. So we can also do plotting, which again is shown in line. So if I run this code chunk down here, you can see that we've got a standard ggplot, and we're doing a histogram. And so you can see that we get 2 lines of two sort of output windows here that we can choose between. So we get our output from our R console, which is the warning that the histogram spits out, which says that it's using 30 bins. Pick a better value with bin width. We'll get to that in a moment. And then we have our chart. Okay, so the nice thing about R Markdown is that it's kind of a self-contained document of the work that you've done in a particular set of analyses, both with the writing that you make about it and with the code in line, and of course the output as well from that code. So we'll get to histograms in a moment. But what we want to do before we get to that is just how do we then compile this document into something that we can then give to others. And so we do this via the knit button. So knitting the current document uses the knitter package, and that basically goes through and runs the code blocks from top to bottom inside a new R session with a clean slate. So we're starting from scratch. There's no variables, data, or packages loaded. That's to ensure that it's reproducible. And then each R chunk is run in turn from the top of the document to the bottom, and the output is then put in line. And it combines everything to produce a document. So I'll press that button now. So you can see that the render tab has come up down here, and it's doing some work. And then it pops up with a window, which is like a browser window essentially. And we have our code output here. So you can see here that I've got a title. There's my introduction there, which is my level 2 heading. You can see that there's the bold and there's the italics. There's our bullet points, our headings, our subheadings and sub-subheadings and so on. Here's our code along with the output from it. So there's the head data, there's the tail, and so on. And there's our histogram in line as well. So it's quite a nice way of producing a single document. Now that HTML file, lab3.html, is just next to, it's in the same folder as the RMD. And it's a self-contained file that we can then give to someone else. So all of the images and so on are inside that HTML document that you could then display in any web browser and so on. Now there are a number of other formats that you can knit to as well. So you can go to PDF and to Microsoft Word. You can also, in certain contexts, go to a PowerPoint. If you're doing a presentation, you can go to PowerPoint as well. I recommend just sticking with HTML, mostly because everyone has a browser, so you can always give it to someone else because it is an HTML document and they'll be able to read it in their browser. Obviously, you can do that with PDF as well, but the trouble with PDF is that on some systems, particularly Windows computers, which of course many of you will have, you need a bunch of extra stuff installed to go to PDF. So knitting to PDF, while it will work fine on this computer, because I've got all the LaTeX stuff installed, just so that you can see what it's like. There's the PDF version of that same document. Okay. Requires some extra stuff installed on your computer, and that extra stuff is great when it works, but is often can have problems that are potentially hard to resolve. So my recommendation is to just stick with HTML and you'll have basically no problems at all. So you might like to take a look through the file and have a play with the markdown syntax to get various things bolded or in italics or written in a code font and so on. There is an R Markdown cheat sheet available under the help menu, and there's also a lot of assistance available online, obviously, for this particular format. The code block right at the top, this one here, is called the metadata block, and it's denoted again by some special characters. So we have 3 dashes at the start and the end. And then within that is a metadata language called YAML, which stands for yet another metadata language, and it consists of some some key value pairs. So we've got title with a colon, that's a special character again, and then we've got a character string specifying what the title is, and then we've got some output stuff. So yours will look a little bit different because it won't have the PDF document thing that was added when I knitted it to PDF earlier. If I knit it back to HTML, you can see that it swaps around. And we can add other fields. So for example, we could add the author field, my name here. Right, I guess I should actually put my name, shouldn't I? Okay. And then when I knit it now, you can see that I have that title, and there's my name underneath. Okay. And there are various other fields that you can use. The main thing to avoid is the use of the colon. So if you want to have a colon in a label, just make sure it's in quotes, like I've done here. So this one here, I use a single quote, and so that colon is sort of ignored, if you like. And here if you use double quotes, doesn't matter as long as you're consistent. Okay. So now we're going to have a look at the distribution of numeric variables, and we're going to start by sort of re-looking at that histogram. So let me redo it here so we've got it in line. We're just going to get rid of the bins argument. Just so I don't have to scroll up all the time. So you can see that there's we've got this histogram here. Okay, so a histogram is a way of presenting the distribution of the values that a numeric variable takes. So in this case, we're looking at the magnitude variable. So that's what we put in our aesthetics. So we had the x-axis mapped to the magnitude. And you'll note we only have an x, we have no y. And so the y variable, the height of the bars here, has been computed for us. Okay, and the computation is reasonably straightforward. What it does is it divides the range of the magnitude variable. So magnitude varies from 4 to around 6.5. It divides that range into small intervals or sub-ranges or bins, and then it just counts the number of earthquakes we have in each bin. So for example, this first bar here is capturing the 4.0 earthquakes, and you can see that the height of that bar is 46, right? That's the count. And if you have a look in the data, the quakes data, then you can see, and if we sort of order it by magnitude, then you can see that we've got about 20 odd there, and then if I scroll down a bit, we have about another 20, and then a few more. So that's where the 46 is coming from. Okay. And so what you get from that is you get an indication of the number of earthquakes of each of the different possible magnitudes as a bar chart, essentially. Okay, so it's a bit different to a bar chart in that it's charting a continuous measure. So the intervals here form a continuum. Now you'll see that there's some output here saying it uses bins equals 30, pick a better value, and that's just because the histogram function is a bit dumb in that it doesn't make any choice at all other than choosing 30 as a default as to the number of bins to use. And the number of bins to use makes a difference to the shape of the distribution that you might get. So in the second piece of code, we've specified that we want 20 bins. And then we get something that looks quite a bit different. So there's the shape that we get with 20 bins. And you can see that that looks quite different to the shape that we got with 30 bins. Okay, covers the same range, but of course the counts are different because the width of the bin here is wider because there's only 20 of them, whereas previously there were 30. And we get this odd thing where on this one we have we have some gaps where there are no earthquakes, and here we have some counts that are much higher. And what's going on here is that the earthquake data, the magnitude, has been rounded. Right, so if we have a look in the data, we can see that we've only got 4.0 and 4.1, and then further down we've got 4.2 and 4.3 and so on. Right, so there's no 4.11 or 4.23, okay? And it's that rounding that has produced these kind of odd results, right? Because this bin here is capturing all of the earthquakes that lie between 4.0 and 4.1. And of course there are no earthquakes in that because all the earthquakes are either 4.0 or 4.1 around this value. Right? And similarly here, this is all the earthquakes between 4.5 and 4.6, and there are none. This is all the earthquakes between 5.0 and 5.1. There are none. Right? They're all at 5.0 or 5.1. So that's why we get the gaps in this one, and that's why we get the spikes in this one. So this bar here, that's extra high, is capturing earthquakes from a little bit below 4.5 to a little bit above 4.6. So it's capturing the 4.5 quakes and the 4.6 quakes. So this is kind of like double counting almost, right? In that the 4.6 earthquakes have been included in this and the 4.5 ones, whereas this bar here is only counting the 4.0s. Right? So that's why we get these spikes. So the reason that the data look funny in this case is because the data are rounded, and the resolution of the data is not matching the resolution of the number of the bins that we're using here. Okay, so there's two things that matter when you're producing a histogram. One is the number of bins you use, and therefore the bin width that results. The other thing that matters is also where you start the bin. Okay. So where you choose to put the first bin here, and so you can see that it's chosen a little bit to the left of the first observation. That's usually what it does, okay. But how much to the left should you do? So that makes a difference, as does the number of bins. But typically the number of bins is much more important than where you start the bins. But the most important thing here is that the width of the bins aren't aligning with the resolution of the data because the data have been rounded. Okay, so because the data are rounded, the discretization that the histogram does is not, so because the data are rounded, it is essentially discretized. The histogram is also discretizing the magnitude according to the number of bins or the width of the bin. When these don't align, we get oddness, right? So align them by specifying the bin width to be a similar resolution. Right, so what we could do is we know that the resolution of the quakes data is 0.1, right, and that the difference between any two observations is at most 0.1. So instead of specifying the number of bins, we can specify the bin width. So we could say that the bin width is 0.1, and then we don't get that same feature happening. And in fact, we now get a much sort of smoother, if you like, shape. Right, so because the bin width is 0.1, we cannot get the situation where two different observations, two different magnitudes are included in the same bin, right? Because we know that the magnitudes are distance 0.1 apart. Okay. Now we can still, of course, choose the number of bins because we could make the bin width equal to 0.2 or to 0.3 or to 0.4. Perhaps I might use a different code block for this. So let's convert that to text. And we'll make this a code block. Okay. So we might also try a different number of a different bin width. So let's try 0.2 and maybe 0.3 and maybe 0.4 as well. Right, just to see what happens. Okay, so you can see that there's some different choices here, and you can see that at some point at least you can kind of get the feel that we're losing signal, aren't we? Right, so if we choose a very wide bin width, then here we actually only have 7 intervals in order to count the magnitude earthquake. So what the histogram is doing is it's summarizing the 1,000 observations down to the number of bars that you end up with, or the number of bins. So in this case, we've summarized it down to 7 numbers. And we can get a feel for the shape of the distribution from this nonetheless. We can see that sort of the most popular earthquake size is sort of around 4.5, maybe just a little bit less than 4.5. And most earthquakes are sort of between 4 and 5. Okay, and we can get a feel for the shape, and that the most popular entries are to the left of the plot, and there's sort of a tail that goes out to the right with only a few larger earthquakes. Okay, and we can get that from all of them, but of course, as we increase the resolution of the histogram by supplying more bins or using a smaller bin width, then we can get more signal out of the chart. So, for example, here we can kind of get the fact that perhaps this peak here is not symmetric, whereas that's hard to see on these plots here. I think probably here sort of the best chart is either this one, where we use bin width 0.2, or this one where we use bin width 0.1. I suspect I like this one here slightly better. What I'm trying to do is to get a feel for the shape of the distribution without also picking up noise from the sampling process. So I'm sort of imagining what would happen if I got a different sample of earthquakes from the same population, so from the same area, right? I'm going to have some slightly different earthquakes in my data set, and therefore the counts of each magnitude might be slightly different, right? So the bar heights are going to move around a little bit, and so I'm trying to sort of anticipate how much they might move. So I'm getting a feel for that mostly from the sample size. So I've got 1,000 here. So the heights of these bars is about 100. And so I'm expecting that if I get another sample, then maybe these will change by plus or minus 10 or something like that, perhaps plus or minus 20. So there might be some jumping about here. And in particular, this feature that we see here of the slight peak, sort of a 4.2, more 4.2s than 4.3s, might just be luck, right? It might just be chance in the sample and not actually a true representation of the underlying population. In fact, I'd kind of expect things to be smoother, which this chart might better represent. Okay, so there's a trade-off here between signal, so you get more signal if you use a higher resolution or more bins, and noise, right? You also get more noise if you use more bins. It's the same idea of the bias variance trade-off that we had before, right? So if you imagine getting another data set and you're using a very coarse representation of a histogram, if we got 2 separate samples of the same distribution and we used a very coarse histogram to summarize them, then the counts in each of the bins here are going to be roughly the same in each sample, and so the shape is going to look roughly the same. So there's going to be little variation from sample to sample. But of course, the actual shape here is too coarse. It's not actually telling us much about the actual number of earthquakes of the same magnitude. So for example, this is sort of implying that 4 and 4.1 have the same count, 4.2 and 4.3 have the same count, 4.2, 4.3 and 4.5 maybe have the same count, and so on, right? Which is not the case, right? We'd expect things to be smoother than that, right? So so this picture is biased. It's not right on average because it's getting the counts wrong for each magnitude on average. Wrong. but there's little variation from sample to sample. Okay, this chart over here, where we use many bins, this is getting the counts right on average, right? It's much closer to the truth of the underlying population, but if I get a different sample, then I expect this chart to change more from sample to sample. So this chart here with many bins, the estimate, if you like, of the population distribution of magnitude is going to have higher variance, but lower bias. So there's a trade-off between these two things. And I think that probably this one here, where we've sort of grouped the magnitudes into sets of 2, if you like, 4.0 and 4.1 together, this is probably a reasonable balance between the two. Now, how many bins you should use in a particular case depends on how large the data set is. So the larger the data set is, the less you'd expect it to change from sample to sample, right? Because each particular sample is representing a greater proportion of the population. So you'd expect it to look a lot more like the population, and therefore if you had another sample of the same size, it would also look a lot like the population. Therefore the differences between the samples is quite small, right? So low variation by default. Therefore you can afford to increase the resolution of the histogram that you're using, right? Because you know that the samples are closer to each other anyway, so you know you're going to have low variance, therefore you might as well sort of err to reducing your bias by increasing the number of bins. Okay, so that's the idea with the number of bins of a histogram. And now how should we describe it? We can see the typical value for magnitude, or so we can see that most earthquakes are between 4 and 5 magnitude, right? So that's your measure of location or center. You could also say with the most popular magnitude around 4.5. So this is the mode. The range is from 4.0 to 6.4. Also, this is measure of spread. And the shape is such that most earthquakes tend to be smaller, and we have just a few large ones. Right, that's your measure of shape. And when you're measuring shape, you're mostly talking about symmetry. So you're looking at, is this a symmetric distribution? And you can see it's not, right? There's a bigger tail out to the right. So you might say that this is skew to the right, or positively skewed is another way to put it. Or there's a long tail to the right, or most observations are on the left and there's only a few on the right, and so on, right? We don't matter quite so much if you get the language correct, as we matter more about do you get the idea correct, right? So do you understand where the majority of the distribution is? Now we've got to be a little bit careful here, I think, in that we're sort of inferring shape from this sample, but this sample has been intentionally truncated, right? There are no earthquakes below magnitude 4.0. And of course, we know that earthquakes exist with a lower magnitude. So you might imagine that there's actually a tail out here to the left that we haven't observed. And if there is, in fact, a tail out here to the left, then perhaps this might be a symmetric distribution that's just been truncated. Okay, so you always have to kind of think about the context and think about, where are the data that perhaps the sample has not picked up deliberately or not, right? So there we go. So that's pretty much answered questions 1 and 2. So whenever we talk about a distribution of a numeric variable, we're looking to summarize a measure of center, so that's where typical values lie, a measure of spread, which gives you an idea of the variation around that typical value, and then a measure of shape, which is saying how that variation occurs. Okay, there's another couple of potential charts for this. There's a density plot. This is one that you may not have seen before. Okay, and it's essentially a smooth version of a histogram. Okay, so what happens here is instead of dividing the range of the magnitude into bins and counting the number of observations in each bin like a histogram does, what we do instead is we drop a smooth curve or kernel of mass, if you like, on top of each observation. So for example, we've got a bunch of 4.0 magnitude quakes, so we drop a sort of a smooth curve, like a little drop of jelly, if you like, on top of the 4.0 for every earthquake. So we'd be dropping 46 on top of 4.0, and similarly we'd be dropping 60 odd or whatever it is on top of 4.1. And where there's many earthquakes close to each other in magnitude, those sort of mounds of jelly, piles of jelly that we're dropping, mount up into mountains of jelly, right? And you get a big mountain shape like this. So this is capturing high areas of high density, so areas where there's lots of earthquakes of a similar magnitude. So it's capturing the same shape as this histogram is doing, but it's done so in a smooth way. Okay, so I tend to like these pictures a little bit more because they're not as jagged, right? There's not that noisy component from the discretization of the histogram. Instead, we've got a kind of a smooth indication of what's going on. Now, the y-axis here, again, is not defined, right? It's computed from the x, and that's done using a kernel density estimator, and it's done in such a way that, I mean, the scale on here is sort of a little bit arbitrary, right? So on the histogram, it was counts, so that kind of made sense. It's the number of earthquakes, right? Here, that doesn't really apply, right? Because we don't actually have we haven't divided it into ranges or anything. So instead we have this concept of density, and it's done in such a way that the area under the curve here is 1. Okay, so that's where that scale comes from. So it's completely arbitrary in the sense that I could change the scale on the x-axis and it would then change the scale on the y-axis as a consequence. So for example, if I had a different scale for magnitude, so say I multiplied all these numbers by 10, so I would have a 40 magnitude quake and a 45 magnitude quake and so on, then that would divide each of these numbers by 10 so that the area under the curve was still 1, right? And so you can think about these numbers here as being essentially arbitrary, and the scale is what matters rather than, or the height of the curve is what matters rather than the particular numbers. So again, what this is telling me is that earthquakes around 4.5 are sort of the most popular. They're the thing that you've got to see the most frequently. Most earthquakes are between say 4 and 5.5 or something like that. Okay, the distribution ranges from 4 to 6.4. We can see the range just as easily, and we can see the skewness, right? We can see this idea of things not being symmetric. Okay, so our conclusion regarding the shape of the distribution is the same. So measure of center would be magnitude 4.5. So that's value of highest density. Or most earthquakes, or earthquakes are typically between say 4 and 5 magnitude, right? And then the range is from 4.0 to 6.4. You don't have to be exact about these numbers. 4 to 6.5 is fine. The shape is asymmetric, with most observations, most earthquakes being smaller, with fewer large ones. Right. So we're conveying the general impression in just that's 3 sentences. Okay, 2 sentences is fine as well. That's the idea when you describe a distribution. Now the density plot there does still have a choice about the construction of it, because one of the things that you've got to choose when you do a kernel density estimate, this isn't a choice that we've made, it's a choice that's been made for us, is you've got to choose sort of how large the blob of jelly that you sort of splotch onto each of the earthquakes is. In particular, you've got to choose the shape of that. So is it a sort of a tall, skinny thing? If it was a tall, skinny thing, then you might expect that you'd get more detail. Or is it a big flat pancake? If it's a big flat pancake, then you'd be sort of smoothing over everything and get less detail. And you can play around with that with the adjust parameter. Okay, so adjust equals 1 is the default, right, which gives us that same image that we had before. But we can apply smaller values, so smaller values would give less smoothing, or larger values which would give more smoothing. All right, so let's run that and see what happens. Okay, and you can see that, so that's our default. This is with less smoothing. So you can see that we have a less smooth curve. And then this is with more smoothing, and you can see that we've smoothed things over more. Right, so here you can see that we've probably smoothed things too much, and that this peak here is starting to look quite symmetric now. We're losing a bit of shape information. Whereas this one is probably undersmoothed, that we're getting all of these sort of wobbliness, which probably don't exist in the population, right? And if you think about the actual distribution of magnitudes, you'd expect them to be somewhat smoother than that. Okay? So sort of in between these two, which of course this one is perhaps optimal. So it's worth having a play when you get a data set with the adjust parameter, just to get a sort of a sense for how much the picture changes as you change that bandwidth parameter of the amount of smoothing. Again, we'd summarize these charts in the same way, and this is a bias variance trade-off here in the same way, right? So as we reduce the adjust parameter, so we make the bandwidth small, we're getting more detail. But at some point, that detail is essentially noise, right? And if it's noise, then it's going to be high variance. So we're sort of increasing the amount of detail or signal, so we're going to decrease the bias, but we're also going to then be increasing noise, which is variation, right? This one here, we're decreasing the amount of information that we're getting from the data, so we're increasing bias, right? It's getting more and more biased because we're getting further away from the actual data, but we're super smooth, so sample to sample variation is going to be super low, right? So we're going to have low variation. There's no noise here, right? That would introduce variation. So again, there's a trade-off. Right? I think this one here balances things out, but you might want to try values that are a bit closer to 1, right, and to see what happens there. The next one is a box plot. Okay, so here's the box plot here. Again, I haven't specified y, only x, so the y coordinates here have been inferred, and in fact, in this case, are completely arbitrary. Okay, and in fact, meaningless. The y coordinate here is just really telling you how wide this box is, and how wide that box is does not matter. So the box plot is generated from the 5-number summary, which is the minimum, which is this value down here, the maximum, which is that value up there, the median, which is the one in the middle, so that's halfway through the data, which is this line in the box here, the lower quartile and the upper quartile. So you can infer from this that there's half the data in the box, because 50% of the data lie between the lower quartile and the upper quartile, 25% between the lower quartile and the median, 25% between the median and the upper quartile, 25% above the upper quartile, and 25% below the lower quartile, right? So this has just divided the data into 4 equal chunks in terms of the number of observations. Now you can see that they're not equal in terms of the length of them on the plot. So that's telling us something about shape. So this is telling us that we've probably got a long tail out to the right, and so this is sort of skewed to the right, right? The box is on the left of the chart, and the box is typical values. So it's telling us about a measure of centre, which is here, about 4.5, 4.6 or so. It's telling us about a measure of spread from the length of the box and the length of the lines on either side. These are sometimes called whiskers. And it's also telling us about shape. Okay. So, yes, the conclusion is the same. Is at about 4.6 magnitude, and measure of spread is similar. So most quakes between say 4.2 and 4.9 magnitude, so that's in the box. And measure of spread is similar from 4.0 to 6.4. Shape can also be inferred from the position of the box compared to the range. Okay, now what about these points out here to the right? So these are marked extreme observations, and the way it does this is arbitrary. So you shouldn't read too much into this. How it does it is it takes the interquartile range, which is the length of the box here. So that's the distance between the lower quartile and the upper quartile, and it then stretches that by 50%, which is the arbitrary nature of things. And then it measures that from the end of the box. So we take this distance here, we stretch it out a bit, and we measure it from here, which gives you sort of an imaginary limit up here, imaginary line if you like. Then any observation past that line is then marked individually as points. The line is then taken up to the first observation that is inside that cutoff. We do the same on the bottom end, but of course, that would be out here somewhere, and there are no observations past that, so we don't need to mark them individually. Now that is arbitrary, so you shouldn't call these outliers, right? But in some cases, they might be outliers. In this case, they're not, right? They're just large earthquakes, no big deal. But in some cases, you might get a very odd observation in your data that you might want to look into that might be sort of at the extreme end. In this case, probably not, right? It usually happens when like the line is quite short and you've got a huge gap and then just sort of one observation that's quite extreme. In that case, you need to sort of look into it. But, if you've sort of got a continuous, dots every now and then it's probably just a long-tailed distribution. Now, obviously, we can change other things on the plot. We can put colors and so on, right? So let's have a look at them on those different charts. So let's have a look at the box plot. The histogram. And the density. Right, let's do our histogram with the correct bin width. Maybe we'll do 0.2. And then we'll add some colors. So let's choose, say, blue. And we'll do a fill with, say, yellow. Okay, and we'll do that for each of them just so that we can get an idea of what that changes. And there they are, right? So the color is the outside, right? So the blue color is the sort of the outline of the various shapes. Okay, and the fill is the inside. Okay, so that's fairly clear. If for whatever reason you don't want an outside, you can change it by just making it transparent or the same color as the fill. So for example, if I wanted the density without a color, I could put the color as being transparent. Right, and then it produces one without the outline of the color, which can be quite nice in some cases. Right, so that's how we change color. We might want to have a look at some other ones. So let's have a quick look at the depth. Okay. So let's start by looking at a box plot, perhaps. So we'll have a look at the depth. So here, there's our box plot. So we can see that that most earthquakes are between about 100 and 500 or so. The range is from maybe down at 50 or something to over 600, and it's reasonably symmetric, isn't it? I guess it's not super symmetric in here. And if we wrote that, that would be completely wrong. And the reason it's completely wrong is I've made some inference from the box plot that isn't true. In particular, from a box plot, you tend to sort of infer shape from it. In particular, I'm sort of inferring that there's a single bump, right? There's a unimodal distribution that we just sort of have it rise up to some area of high density and then fall off again. And in many cases, that's the case, right? So back in this case, this box plot here, there was nothing wrong about that because that is in fact how the data was shaped. But in this one down here, it's wrong because we've actually don't have a unimodal distribution. And we can see that from a histogram or a density. Right, and we can see that the histogram actually shows that there's very distinctly two bumps. Okay, the density plot shows us the same thing. Okay, so the inference from the box plot is that this is sort of in about 300 odd is sort of typical values of depth, if you like. The histogram shows us that within about 300, that's actually typical values where you don't get an earthquake, right? You get earthquakes at either very shallow, maybe there's another bump at about a couple of hundred, and then you get some that are very deep. You don't get many earthquakes in the middle. Okay, but we can't infer that from the box plot. So the box plot should really only be used if you've got a unimodal distribution. Okay, so let's just add a comment about that. So it's important when using box plots that the inference from them, i.e. what your reader takes from the plot, is that the distribution has one peak or is unimodal. If this isn't the case, the box plot may misinform. And another plot would be better. Histogram, density, etc. Okay, in this case, we see there's two modes, or possibly more, i.e. earthquakes are either shallow or deep, and there aren't many in the middle, which is where the box is on the box plot. Okay. So when we're describing this shape, we're going to point out the fact that there's two peaks, right? So we can talk about, typical values aren't in the middle anymore. So talking about the median or the mean wouldn't be representative of typical values. The typical values are actually in the two modes. Okay. So you just got to be a bit careful about that. So I encourage you to also look at the number of stations and see what your conclusion about that is. So now we're going to go on and we're going to say, okay, we've looked at the situation where we have a single numeric measure, and we've also looked at the situation where we have two numeric measures. We did that with scatter plots, for example. The interesting thing there, of course, is how one changes with the other. So is there a trend, for example? What if we've got a numeric measure and then a grouping variable? Then what we want to know there is there differences between the groups in terms of the numeric measure? So does the sort of the size of the earthquakes differ based on that grouping variable? And so we're going to create a new data set or a new version of the same data set by using the mutate command to create a new column called how deep. And how deep is going to use the rule, if the depth is less than 300, call it shallow, and if the depth is bigger than 300, we'll call it deep. So this is taking the information that we've got from this chart here, right, and said basically there seems to be kind of two groups here, so we're going to split it into two groups. And then we've got a grouping variable that we could then look at to see whether there's a relationship with the other, with the magnitude, for example. Right, so let's run this code. Okay, so here's the quakes cat. So you can see that we've added this new column, how deep, and you can see that it's deep when the depth is is a large number, and it's shallow when the depth is a small number, right? Kind of makes sense. And then we've done a box plot by adding the how deep variable in the y aesthetic. So in the box plot, remember the y was meaningless. So we can utilize it, right, in the box plot. And this then produces side-by-side box plots that we can then say something about. So you can see here that the shape of these distributions is similar, right? And the box in both cases is on the left. The spreads are also similar in that the length of the boxes are about the same and the length of the distribution, the ranges of each are about the same. I mean, there's a little bit of difference maybe, but they're essentially the same. But there's been a shift, isn't there, right? In that the shallow earthquakes have a larger magnitude than the deeper earthquakes, right? So our conclusion might be the shape and spreads of the of earthquake magnitudes of shallow or deep earthquake magnitudes are similar. Most earthquakes are smaller and a few larger. The ranges are pretty similar, 4 to 6 or more, right? However, the typical values or measure of location differs. Shallow quakes tend to be a bit larger than deeper quakes, right? So when we're looking at the distribution of a numeric measure by group, then you do all of the same things you would for a distribution of a numeric measure. So you look at center, shape, and spread, and then you look at how they differ between groups, right? So that's the added sort of ingredient. And a box plot is great for that because you can put them side by side. And it doesn't really matter how many groups you have, right? You can just sort of stack them up. So box plot works really well when the data are unimodal, right? There's only one peak, so the inference from the box plot that there's only one peak sort of holds. And then you can just sort of compare across them quite easily. We can also use color, so we can use any other aesthetic that we like, right? So obviously for the histogram and the density, we won't be able to use the y-axis because that's already been computed for us. But we will be able to use other things. So for example, we could use color for how deep as well, right? And we'd get two different colors. And of course the guide here isn't strongly useful because we've got the x-axis here, but you could use it instead. You don't need the y, so you could just use color. In which case you've got that odd y-axis that is kind of meaningless, but nonetheless you've got separation by color, and the guide then makes sense. We can use fill, which will of course color in the box plot instead. And we could also do this for histograms and densities. Okay, so if we also had y here, right, then we might want to turn that guide off. So we want to say the fill guide is none to turn that off, right? You could just Google that and that'll come up as the first hit. Okay, on how to turn a guide off in ggplot or how to turn a legend off in ggplot. And so there we have it if you want to add a little bit of color. So we can also do this with the histogram and the density. We'll do the density first. Okay, so we could use fill. So there's the density. We could also use color. Right, so if we don't want them filled, so the advantage of color is you can see through them. We could do that with fill as well, but we need to add some transparency, right? So we'd make them partially transparent. And that's a nice way of comparing two groups, right? We get the density, so we get more information than we do off a box plot because we can infer shape, and if there's if it was bimodal, we could see the fact that there's two peaks or whatever. And our inference is the same, right? In that the shallow earthquakes are shifted up, right? Shallow earthquakes tend to have bigger magnitude than deep earthquakes. There's some overlap, obviously, right? So there's some small, shallow ones and some large, deep ones. But in general, there's a shift to the right. Okay, so that tells us something about that. We can do it with histograms as well. right, let's see what happens there. So with a histogram, we get this shape here. We're going to have to change the bin width, aren't we? So we get this shape here. And what you'll notice is that the shape I have here, you can infer it from the counts as well. You know, I've got 100 here and almost 200 here. So you can see that if we just look at sort of the curve made by the top of the red here, there's probably about 1,000 earthquakes there, aren't there? So we've got a couple of hundred here, a couple of hundred there, 180 there, 100 there, over 100 there. It's going to add up to about 1,000. So what's happened here is that it's gone and split the data into the bins and counted the number in each bin of each type and coloured them accordingly. So there's actually, you know, about 40 odd, I guess it's maybe 35 shallow earthquakes of size 4.0 and 4.1, and there's about 70 odd deep earthquakes, and it's just added them on top of each other. So this is like a stacked bar chart. So we can't actually infer the distribution of the red because it's starting at the top of the distribution of the blue, right? And we could see this if we added some transparency, right? So if we put some transparency in there, then you can see that the whole thing just becomes transparent. You can't see under the blue that there's red. There's no red under there at all. The red starts from on top of the blue, right? So, so a problem with the histogram is that the bars stack. So you only truly see the shape of the group that starts at the at y equals 0. The other groups start at the top of that group, right? So we can use the position argument to change this, right? So let's do that. Look at our histogram. Okay, and we're going to use the position argument. And we could have position equals dodge is one option. Okay, let's fix our bin width again. Okay, and so what that does is it essentially starts them both at 0 and just shifts them slightly and makes the bars half width so that we can see them both side by side. So I don't really like this chart because it sort of your inference might be that there's sort of no blue ones in between this one and this one, which of course isn't the case. So I actually prefer position equals identity, which starts both at the origin. So starts both at y equals 0. So now they are smacked on top of each other, so we're going to have to add some transparency. So that we can see through, and you can see that they're now overlapping. Okay, so this one, side by side histograms, not preferred. One on top of the other, add transparency. Okay, so I like this one better, and again the inference is the same, right? The shallow quakes have moved up, tend to be higher magnitude than the deep quakes. From the histogram, we can also note that there are more shallow quakes than deep quakes because the blue tends to be a bit higher than the red, which you don't get from the densities. Because both curves have area under the curve equal to 1, right? So the total has been factored out, if you like. Whereas in the histogram, you do get that information. So there's always trade-offs with the chart type that you choose. I personally prefer densities just because I like the smooth nature of them rather than the histogram. But more people have seen histograms, so will get the inference from the chart, perhaps, than than with the density, because fewer people have seen the ideas of density, and the idea of distribution and so on is a little bit less well known. So at the end, you might want to add some better labels to these, and then we'll just knit the document and make sure that it all works. And we haven't made any errors. So that seems fine, and there's the document there, and we can scroll down, and there, of course, is all our charts.